Today, we will talk about the study about the electron pairing symmetry in recently discovered Kagome superconductors. We used low temperature and laser-based ARPES to study these Kagome superconductors, and these results were published in Nature and Nature Communications. So let me start from the introduction of Kagome lattice. A Kagome lattice is formed by corner shared triangles. Such a spatial lattice provides an ideal platform to study the interplay between the correlation, band topology, and the lattice geometry. Because there are Dirac band and a flat band and Van Hove singularities in its electronic band structure, shown in this figure. So interplay of these Van Hove singularities will introduce the nesting of Fermi surface and stimulates the electrons to form a charge density wave and superconductivity in low temperatures. So the AVS system is the first non-magnetic Kagome superconductor. It has a layer structure, including a vanadium antimony layer, shown in this figure, sandwiched by two antimony layers and two alkaline layers. So in the vanadium antimony layer, the vanadium atoms form a Kagome lattice. As the phase diagram shown here, the superconductivity competes with the charge density wave order in an interesting way. Double superconducting dome will appear with the charge density wave order being surprised. So this study will focus on the CVS compound, which has a CDW transition temperature at 94 K and the superconducting transition at 2.5 K. So to reveal the nature of the superconductivity in these Kagome compounds, so we studied the electron phonon coupling as well as tested its relationship with superconductivity. And besides, we also measured the superconducting gaps in momentum space, which gives us the pairing symmetry and helps to narrow down the possible pairing mechanism. Our tool is the so-called angle-resolved photoemission spectroscopy. As the measured intensity by this formula, we can study the electron phonon coupling from the safe energy function and extracted the superconducting gaps from the electronic energy distribution at different momentum. The first part is to test the electron phonon coupling for superconductivity in CVS compound. So first I show the Fermi surface mapping here. There are three Fermi surface sheets. We named them as alpha, beta, and delta. The ARPES spectrum of this example cut is showing this figure. So clearly there is electronic kinks in the band structure. So by analyzing the momentum distribution curves, the safe energy is extracted in this figure. And we can find a peak in the real part and a step jump in the imaginary part at same energy. These features are consistent with the simulation result and suggest a coupling between electrons and a bosonic mode at a frequency of around 30 millieV. So the candidates of this bosonic mode could be a magnon or phonon. First, there is a non-magnetic order in this material, so we exclude the possibility of magnon. Second, this kink is persistent above the CDW transition temperature as shown in these figures. Therefore, we conclude that this electronic kink is induced by electron phonon coupling. Furthermore, we carefully study the orbital and momentum dependence of electron phonon coupling. We study the orbital dependence of electron phonon coupling by comparing the electronic kinks on the alpha and beta band because these two bands are derived from the different orbitals. So from the extracted band dispersion and the real part safe energy, we found a kink around 32 millieV dominant on the alpha band and two observed kinks near 10 and 32 millieV on the beta band. So through fit these real part safe energy, we extracted the Elastiberg function and present them in this figure. And we found that there are two prominent phonon modes strongly coupled with electrons. Interestingly, even though the distribution of these two phonon modes are different on different orbitals, their total electron phonon coupling junction are quite similar, as shown in this figure. Here we use the two methods to extract this electron coupling junction. One is the integration of the electrical function, and another is the slope of the real safe energy at EF. Consider experimentally errors. The extracted electron phonon coupling junction by these two methods is comparable. We also study the electronic kinks along the alpha and beta Fermi surfaces to study the momentum dependence. And it turns out that the electron phonon coupling junction is isotropic in the momentum space and averaged at 0.6. So with the experimentally extracted electrical function and the electron phonon coupling junction, we can estimate the supersonic transition temperature driven by electron phonon coupling based on the Macmillan's formula. The main parameters are and the estimated TC is shown in this table. So it shows like estimated TC from electron phonon coupling junction is on the same magnitude order with experimental TC. So implying the electron phonon coupling could be enough strong to support the superconducting transition. To further examine this speculation, we studied the electron phonon coupling in a substitute CVS superconductors with a higher TC. So we found the electron phonon coupling is selectively enhanced to be twice on the vanadium 3D orbital derived beta band. So this enhanced electron phonon coupling can also support its superconducting transition at a higher temperature, as shown in this table. So this result further highlights the importance of the electron phonon coupling on the superconductivity of the CVS material. So let's summarize this part. We used the laser-ARPES, based ARPES, and the electrical function analysis. We determined an intermediate electron phonon coupling junction for this CVS superconductor. So this value is twice large than the value predicted by density function theory. And such an electron phonon coupling can support a Macmillan superconducting transition temperature on the same magnetic order of the experimentary TC. So, and the electron phonon coupling displays an enhancement around the 10 MeV and on the vanadium 3D electrons of isovalent substitute CVS superconductor with a higher TC. And our result together highlights the important role of electron phonon coupling on the superconductivity of CVS. Okay, then we directed to detect the superconducting gap structure in the momentum space. So to overcome the challenges from the low TC of the Princeton superconductors, we choose the substitute CVS by niobium and the tantalum atoms, which has a higher TC. Their phase diagram are shown in this figure. So among them, we choose two exemplary substitutions, the 77% niobium and the 15% tantalum substitutions, because they have a relative high and similar TC, and the CDW order is partially surprised in 7% niobium substitution and fully surprised in 15 tantalum substitution. So this enable us not only to detect the superconducting gap symmetry, but also study the influence of the CDW order on the superconducting gap symmetry. So we first show the superconducting gap in the momentum space of the 14 tantalum doped sample. So the three Fermi surfaces sheets can be distinguished well from these ARPES intensity maps, this ensures the precise determinations of the Fermi momentum. So we first measure the temperature-dependent EDC energy distribution curves at a specific momentum, as shown in this figure. It shows the superconducting gap is gradually closed with increase in temperature. So we extracted the fitted gap size and plot them in this as a function of temperature. A BCS fitting fit to the least temperature-dependent gap shows the Tc is around 5.2 K, which is highly consistent with the Tc determined from the bulk resistivity measurement. So the finite gap in the EDCs at the temperature close to Tc proves the energy resolution is enough high in our measurements. Then we present the EDCs at Kf taken along with alpha, beta, and delta Fermi surface here. The EDC was taken in 2K and 7K for the precise in situ comparison. So the coherent peaks and the leading edge shift are clearly seen in all these EDCs at 2K, indicating a nodeless superconducting gap. All these peaks are located around 1 meV below EF, and the fitted gap are plotted as function of Fermi surface angle in this figure. It shows a nearly isotropic and has an average value around 0.8 meV. This gives a ratio of 2 delta of kbTc is about 3.44, which is close to the BCS value 3.5653. So it hints at a weak coupling superconductivity. And next, we present the superconducting gap results of the 7% Niobium doped sample, which shows a CDW order above Tc, as showing the resistivity transport measurements result here. And compare the EDC with the tantalum doped sample, the coherent peak in niobium doped sample is slightly weaker. It is possible because of the low Tc and a smaller gap. But still, the leading edge shift and can be seen in all these EDCs. So through fitting, the superconducting gap are extracted as function of the Fermi surface angle is shown in this figure. So the superconducting gap remains nodeless and nearly isotropic in 7% niobium doped sample. So the gap size is averaged around 0.55 meV, giving that the 2 delta of kbTc is about 2.83, slightly lower than the BCS value. It means the superconductivity is still in a weak coupling regime, and the relative low 2 delta of kbTc could be because of the competition between the CDW and the superconductivity. Since there are finite band dispersion along z direction momentum in these CVS superconductors, therefore we also check the superconducting gap along kz direction by tunneling the photon energy from 5.8 eV to 7 eV. The measurements were done in niobium doped sample. The Fermi surface mapping and the EDC taken along the hexagonal Fermi surface is shown in these figures. Because the energy resolution with 7 eV laser is not good as the one with 5.8 eV laser, so the EDCs measured by 7 eV laser looks like much more broadening. However, by symmetrizing the EDCs, we found the density of states is missing near EF at low temperatures. So as shown in this figure, so indicating a finite gap opening. With the energy resolution considered, as shown in this figure, the fitted superconducting gap is similar with the one measured with the 5.8 eV laser. So this result suggests that the superconducting gap is Kz independent within our experimentally errors. So therefore, by measuring the superconducting gap in a full momentum space, we reveal a robust isotropic superconducting gap with or without CDW order, and we summarize these results in this figure. So considering the time reversal symmetry breaking CDW order, we were motivated to check the time reversal symmetry of the superconducting state. To eliminate the influence of the CDW order, we performed the muon spin relaxation rate measurements to check this on the CDW fully surprised 14 tantalum doped sample. So these results are showing these figures. So it shows the increase of muon spin relaxation rates when entering the superconducting state, so which can be viewed as signature of temporal reversal symmetry breaking. Therefore, our combined ARPES and muon spin relaxation results together suggest the isotropic and time reversal symmetry breaking pairing states in these CVS Kagome superconductors. that is the Carroll D plus ID or S plus S pairing symmetries. Let's summary the second part. So our high-resolution ARPES measurements provide for the first time a directly characterization of the nodal-less isotropic superconducting gap structure in the momentum space of CsV3Sb5-derived Kagome superconductors. More importantly, we confirmed this superconducting gap structure is robust with or without CDW order. So this advanced our understanding of the interplay between the superconductivity and the CDW order in these Kagome superconductors. Moreover, the supplementary muon spin relaxation measurements shows increased zero muon spin relaxation rates across the superconducting transition temperature in 14 tantalum substitute CVS, imply a time reversal symmetry break inside the superconducting state. So the combined results reveal an unconventional electron-phonon pairing in these Kagome superconductors, at least for the CVS with CDW order surprised, and suggesting a possible candidate pairing of S plus IS wave or Carroll DOP wave. In the last, I would like to thank all my collaborators in these famous institutes or universities around the world, and thank the support from these funding organizations. That's all. Thank you for your listening.